So in this lecture, I'll continue on the topic of weak and strong convergence in LXY. So X and Y will be Banach spaces, and we will represent by M the bounded linear operators from X to Y. So let me start with a theorem which is a consequence of the principle of uniform boundedness, and it can be stated as follows. You consider a family M alpha of bounded linear operators. So each M alpha belongs to LXY. And here the set of indices I can be uncountable. It's any set. And I assume that for any x in X and for any L in Y prime, if you apply L to the point M alpha X in Y, that I will assume that this is bounded. So that there exists a constant which depends on X and on L, such that this quantity, it's bounded uniformly in alpha. And what I claim is that it follows from this assumption that this family is actually uniformly bounded, so that there exists a finite constant C naught such that the norm of M alpha, it's bounded by C naught for all alpha in I. And, well, to prove this theorem, we will use the principle of uniform boundedness. So let me start by fixing X. So let's fix X in X. And let's consider Y alpha to be M alpha X. So this is a family of points in Y. And what this condition is telling us is that for all L in Y prime, this is Y alpha, so there exists a constant C of L, such that Y alpha L, it's bounded by this constant CL for all alpha in I. So we have a family of points Y alpha in Y. This family, it's uncountable. And what we know is that if we apply L to this family of points Y alpha, the absolute value of L of Y alpha, it's bounded by a constant which depends on L but does not depend on alpha. So it's uniform over alpha. And we have seen in a previous lecture that in this case, this family of points Y alpha is actually bounded, so that there exists a constant C such that, let me call that C1, such that the norm of Y alpha, it's bounded by this constant C1. But what is Y alpha? Y alpha, it's M alpha X, so this holds for all alpha in I. So what we proved is that M alpha X, it's bounded by a constant C1 for all alpha in I. So that for each fixed X, so we fixed an X, for this fixed X, of course, this family depends on X. So we have a family of points in Y which depends on X. And we proved that this family is bounded. Of course, this constant C1 may depend on X. So actually, this constant C1 may depend on X. And so we proved that for any X in x, there exists a constant C1 which depends on x, such that the norm of M alpha x, it's bounded by C1x uniformly over alpha in I. So up to now we proved that for any x in x there exists a finite constant C1 of x such that the norm of M alpha x, it's bounded by C1x uniformly in alpha. Now we can complete the proof by defining a function f alpha of x which is given by the norm of M alpha x. We have seen that these functions, in the previous lecture we proved that these functions are subadditive, they are positive homogeneous, and that they are continuous. And moreover, here we are saying that they are pointwisely bounded, so that for any x there is this constant C1 of x, such that f alpha of x, so f alpha of x, it's bounded by C1 of x. And we proved in the previous lecture that if we have such a family of subadditive, positive homogeneous, and continuous functions which are bounded pointwisely, then there exists a constant C0, finite constant C0, such that f alpha of x, it's bounded by C0 times the norm of x for all alpha in I and for all x in x. So this result has been proved in the previous lecture, has been used in the previous lecture, last lecture. And, well, but what is the norm of f alpha x? Well, f alpha, it's positive, so this is just the norm of M alpha x. So this is bounded by C0 x. This inequality holds for all x in x. So this implies that the norm of M alpha, it's bounded by C0, and this holds for all alpha in I. So we proved that there exists this finite constant C0 such that the norm of M alpha, it's bounded by C0 for all alpha in I. And this is exactly what we wanted to prove. Well, a simple consequence of the previous result is the following. Assume that you have a sequence Mn of bounded linear operator which is converging weakly to some operator M. What does that mean? That means that, so these operators M and Mn are functions from x to y. So weakly converging means that for all x in x, M and x converge weakly to mx. So now these are points, M and x and mx are points in y. And the fact that this sequence of points is converging to that sequence means that for all L in y prime, M and x L converges to L mx. So we know that for all, if Mn is converging weakly to M, we know that for all x in x and all L in y prime, this sequence is converging to that one, and since this sequence is converging, this means that this sequence is bounded. So this means that there exists a finite constant C such that Mnx L, it's bounded by this constant C. Of course, this constant C may depend on x and L. So let me present this dependence on the notation, introduce that dependence on the notation. So there exists a constant C which depends on x and L such that the absolute value of L applied to M and X, it's bounded by this constant C, but that holds for all N. And this is exactly the assumption of the previous theorem. We have that for all X in X, L in Y prime, there exists a finite constant CXL, such that this sequence of numbers is bounded by that number. And so by the previous theorem, this tells us that actually the sequence of bounded linear maps, it's bounded. So that there exists a finite constant C such that Mn, it's bounded by this constant C. So we have just proved that if a sequence of bounded linear maps Mn converge to M, then it is bounded. So now let me discuss composition. So we have three Banach spaces X, Y, and Z. And we have a bounded linear map from X to Y and a bounded linear map N from Y to Z. So I want to define a new linear map, NM, which is the composition of M with N. So this goes from X to Z, and it associates to a point X, the point N applied to MX. So MX, it's a point from Y, and so we can apply N to this point to get a point in Z. So this composition defines a map from X to Z. I leave it to you to check that NM is a linear map from X to Z, and I will show, and this is very easy, that it is a bounded map and that its norm, NM, it's bounded by the norm of N times the norm of M. Well, and this is extremely simple. I want to estimate the norm of NM. So for that, I take X in X. I compute the norm of NMX. Well, this is by definition the norm of N applied to MX. But N, it's a bounded linear operator. So this is bounded by the norm of N times the norm of MX. Now, M, it's a bounded linear operator. So this is bounded by the norm of M times the norm of M times the norm of X. So we have here a constant, C0, and what we just proved is that the operator NM applied to X, its norm, it's bounded by this constant times the norm of X. So this tells us that NM, it's a bounded operator, it's bounded, and that its norm, NM, it's bounded by this constant, and this constant is the norm of N times the norm of M. So this proves that not only NM decomposition, it's a bounded operator, but also that its norm, it's bounded by the norm of M times the norm of M, as we claimed. And now, well, we have a bounded operator NM. We can define its transpose. So let me represent NM prime, the transpose of this operator NM. And I want to prove that this transposition is actually the composition of M prime with N prime. So we have M, an operator from X to Y. So M prime is now a bounded operator from Y prime to X prime. And we have an operator N prime, which is a bounded linear operator from Z prime to Y prime. So I can take the composition of N prime, which sends Z prime to Y prime, with M prime, which sends Y prime to X prime. So this composition is well defined, and we proved, so in the previous argument applied to these two operators shows that this is a bounded linear operator. And what I'm claiming now is that this identity holds, so that if we take the transpose of nm, this is the composition of the transpose of m with the transpose of n. So to prove that, so these are two operators which are going from z prime to x prime. So to prove that they are equal, we have to show that n m prime applied to L, where L it's an element of z prime, that this is equal to m prime n prime L. So now we consider L an element of z prime. We applied nm prime to L. So nm prime is sending z prime to x prime. So this object here, it's an element of x prime, as well as this one. So to show that these two elements of x prime are equal, we have to apply x. So we fix an x. We have to show that if we apply the left-hand side to x, we obtain the same thing as applying the right-hand side to x. So we want to apply x. So let me represent this in this way. So this is n m prime L on the left-hand side. So let's compute the left-hand side. So by definition of nm prime, this is equal to nm x applied to L. So this is the definition of the transpose. So if you take the transpose of an operator and you apply it to a bounded linear functional, this is equal to applying the operator to x and then considering the value of the bounded linear functional L on this point. Well, and so let's compute now the right-hand side applied to x. So this is x m prime n prime L. But n prime, so L, it's an element of z prime. N prime of L, it's an element of y prime. So an element of y prime belongs to y prime. So by definition of m prime, this is equal to mx n prime L. Now L, it's an element of z prime. So n prime L, it's an element of y prime, and this is an element of y. So by definition of n prime, this is equal to n applied to mx L. And you see that the left-hand side which we computed and the right-hand side which just computed, so left-hand side is equal to that, the right-hand side is equal to that. These two expressions are equal. So indeed, we proved that for all x, we have this identity. And since this identity holds for all x, this means that these two bounded linear functions are equal. Since these two bounded linear functions are equal for all L, we have that these two operators are indeed equal. So let me just repeat what we did. We want to prove this identity. To prove that this identity holds, we have to check that for all L in Z prime, we have this identity. This is an identity between bounded linear functional on X. So to prove that two bounded linear functional on X are equal, we have to show that their image at X, it's equal for all X. So we fixed an X, and what we have to show is that these two scalar numbers are equal. So we computed the left side, we compute the right side, and we show they're equal. The left side we computed by using the definition of the transpose, and the right side we computed by using twice the definition of the transpose. since the expression we obtained are equal, we concluded that this identity holds. If this identity holds for all x, we have this identity for all L, and if this identity holds for all L, we have this identity.